All right, so options for finding integrals. So just a review of stuff we've done before we move on to the next section. So one, we have our favorite idea, which is a Riemann sum. I think I put the I and the E in the wrong order. And I know everybody loves Riemann sums, so we'll do some more of those next week, because I know you've been missing them. So we found Riemann sums to be very challenging and not very productive because they didn't work on a lot of functions because we didn't have tricks for evaluating the limit of the sum. So then we discovered the fundamental theorem of calculus. And the fundamental theorem of calculus meant that we could use derivative formulas backwards to calculate integrals. So that was helpful. Every once in a while, though, we hit a function that didn't look like something that we had as a derivative before. And so we would occasionally be able to use algebra to clean up the integrand to make it look like something we recognized, and then we could use the derivative formulas. Algebra, there we go. We then discovered the idea of U substitutions. And they were very powerful in allowing us to rewrite things. So it was kind of a fancy algebra to allow us to use certain derivative formulas. And we had limits to that. Substitutions, does anybody remember what derivative formula substitutions are based on? The chain rule, yeah, that's a result of the chain rule. Soon after that, we discovered integration by parts, which is a consequence of which derivative rule? Anybody remember? The product rule, yeah, it was a result of the product rule. So we're collecting all these tricks to try and figure out what's going on. And sometimes the tricks are based on algebra, like substitutions is a fancy kind of algebra, but it depends on the idea of implicit differentiation and the chain rule. Integration by parts, that required us to reconsider products. And then we started learning other tricks, like, for example, trig substitution. And we actually have different kinds of algebra that we've applied. Sometimes we just applied regular algebra for like polynomials and rational functions. But we also threw in some algebra of trigonometry, right? Using trig identities to rewrite stuff. So that's the collection of stuff we have pretty much in a nutshell, besides applications we've done of integrals. So how to come up with an antiderivative. These are our tricks so far. So we're going to take a look at a new trick today, which is algebra related to polynomial and rational functions that you've kind of seen before, but kind of not. It depends on where you had your college algebra or pre-calculus class. So consider the rational function 1 over x minus 1 plus negative 1 over x. So that's the sum of two simple rational functions. What's the common denominator here? This has an x, and an x minus 1 is fundamentally different factor. So the common denominator would have to be x times x minus 1. So let's consider the common denominator here is going to be x times x minus 1. So I want both of these to have the common denominator. So I'll have to multiply top and bottom of this one by x, and I'll have to multiply top and bottom of this one by x minus 1 to make that happen. Okay, and you probably had this actually in an Algebra 2 class a long time ago. So let's see, when I clean that numerator up, I'm going to get what, an x, and then I'm going to get plus a negative x, and then subtracting negative 1 means I'll get a plus 1. And so when I finish cleaning this up, I get just 1 over x times x minus 1, which we could also write as x squared minus x. So if I had asked you to integrate that with respect to x anytime recently, you know, what tricks would we throw at that? We might try a trig substitution. Now with a trig substitution, we're looking for things like x squared minus a squared, or a squared minus x squared, or what else would we want? X squared plus a squared? Does this look like any of those? It looks like, ooh, that's an a squared, thank you. Yeah, it doesn't quite look like any of those. Could I make it look like one of those? Well, a has to be a constant, so we can't say the square root of x is a. A has got to be constant here. It can't be a variable. Any other ideas? You could try a u substitution here, but that's not going to work. How? Split it into two integrals? How would you split it into two integrals? What's that? Yeah, we just added two fractions and came up with a single fraction. However, from what we just did up there, we know that this is equal to the integral of 1 over x minus 1 minus 1 over x. And we know we can slide an integral, distribute an integral through addition and subtraction. I got a plus and negative 1 there, so I'm just going to write it as a minus. But yeah, it could be the other way. And then that means this is the integral of 1 over x minus 1 with respect to x minus the integral of 1 over x with respect to x. And hey, that's easy. This is just natural log for an antiderivative. So although trig substitution looked promising, and it turns out we actually could use trig substitution on this. There's a trick we could apply. We'll do that later. So here, what am I going to get? I'm going to get the natural log of the absolute value of x minus 1 for an antiderivative, and then minus the natural log of the absolute value of x plus some constant. And the difference of natural logs can be rewritten as the natural log of the quotient. So I could rewrite this one more time and say this is the natural log of the absolute value of x minus 1 over x plus c. Right? And we could rewrite a little more, but I think that's pretty good. Just a note on the integration, the trig substitution idea. We could complete the square on that thing, and then it would look like that guy right there, if we did a complete the square on it. So just quick note on completing the square. It's another algebra tool that could be helpful. So we have x squared minus x. We want to turn that into a perfect square. What's the middle coefficient here? It's -1, right? Complete the square says take that -1 and cut it in half. That's -1/2, and then square it. So I would like to have a 1/4 right there, because that's half the middle coefficient squared. Now I can't just throw that 1/4 in there. I have to say, well, let's take a quarter away to keep things balanced. This thing right here is then the square of x minus 1/2. And then we have minus 1/4 there, which I could write as 1/2 squared. And so I could say this is a u squared minus an a squared. So it turns out I can use trig substitution on this. Does that mean any rational function I can use trig substitution on? Well, no, because sometimes we might have cubes or fourth powers in the bottom, and then that's a problem. But if it's a square, turns out I can usually rewrite the quadratic in the denominator to match one of those guys there. So we have a couple of different tricks. So then the theory goes, if the sum of two rational functions can be a single rational function, then shouldn't we be able to take single rational functions that have products in the denominator and rewrite them as sums of rational functions? And the answer is yes, we can do that. So this is an algebraic technique called partial fractions. Partial fraction. Some people add a word decomposition. Decomposition, I wish that was a cool word. So we're going to look at an algebraic technique called partial fraction decomposition. And there's, I don't know if you remember from your pre-calculus class, but there's what's called the fundamental theorem of algebra. Does anyone remember that? Fundamental theorem of algebra is that any polynomial can be factored into linear and irreducible quadratic terms, is what it says. Irreducible quadratic means that if you like applied the quadratic formula to it, you would end up with i's, complex numbers, in the answer, which means you can't factor it with regular numbers. So what we need to consider then are linear factors and quadratic factors based on the fundamental theorem of algebra. So linear factors could be boiled down to things that look like x plus r. Now, normally we consider linear to be something like ax plus b, but we could divide the a out of that. And so r would be like a b over a. And the a is just some multiple, and multiples and integrals just get carried along, right? So we're not going to worry about that. Let's pull that out. And it could be that this sucker right here is raised to some power. Let's say it's to the power n. If that's the case, then the theory goes that you can rewrite, if that's a factor of the denominator, you can rewrite the rational expression as some number a1 over x plus r plus some number a2 over x plus r squared. And then however big n is, you just keep going with constants in the top, an over x plus r to the n. So that's if you have linear factors in the bottom. If you have quadratic factors in the bottom, oops, I want to switch colors. Then you get something similar. So there we would have something like x squared plus px plus q. So if there was a leading coefficient, we could divide that out. We don't have to worry about it too much. And then the decomposition of fractions is going to give you something like let's call it a1x plus b1 over x squared plus px plus q. So if there's only a single one, you can rewrite it like that, which isn't all that helpful. If that was raised to some power n, then there's going to be a similar to the blue thing up there. It's just going to keep moving along. So we're going to have a plus a2x plus b2 over r quadratic squared. All the way down to an nth one, whatever n happens to be. This all looks pretty crazy in practice. Oops, bn. It's pretty crazy too. Squared, x squared plus px plus q to the n. The nice thing about this, if you think about it with the quadratic ones, if you think about a u substitution, if you let u equal the denominator, then du is going to be linear like the numerator, okay, which is super helpful. So this will take something that we couldn't deal with at first, like this guy right here, and break it down into individual pieces that we can totally handle, either with something like a trigonometric integral, something involving maybe the arctangent, or natural log is going to pop up there too. All right, so let's give a couple of these a try. Which did I think would be a nice start? That one's not too bad. All right, let's suppose we have the integral of x squared plus 3 over x squared minus 15x plus 56. with respect to x. Hello, good, I do have sound still. So the first thing to double check is, now if that were just a linear factor in the top, then I could just use a U substitution and this would work out pretty well. It's not, so I have to do something else. First thing is to look at your denominator and say, does the denominator factor? And we should see that 56 is 7 times 8 and 7 plus 8 is 15. So yeah, this does. So this can be rewritten, and the numerator doesn't factor, by the way. Sometimes that's consequential, but not usually. And so I'm going to have an x minus 7 times an x minus 8 in the bottom. So we fit in the category of the first kind of linear factors. So that means, ignoring the integral for a moment, that my x squared plus 3 over x minus 7 times x minus 8 I should be able to rewrite this as a over x minus 7 plus some b over x minus 8 is the claim here. I just have to figure out what a and b are. All right, there's two ways to do that. Both ways start the same. First thing we want to do is clear all the denominators by multiplying everything by the GCD. So we want to multiply everything by x minus 7 times x minus 8. So we're going to have to distribute that through the equation. When I do that, the left side comes up really nice. It's just x cubed plus 3. On the other side, we get some partial cancellation. So this fraction right here, the x minus 7 divides out, leaving a times x minus 8. Oh, shit, that's a square. Thank you. And then we're going to have a plus b times x minus 7. Two different ways to handle it from here. One way is to pick convenient values of x and see what happens. Like, wouldn't it be nice if x were 7, for example? Okay. So if we do that, if we pick 7 for x on this side, what do we get? If x equals 7, then here we'll get 49 plus 3, which is 52. Equals 7 minus 8 is -1, so I'll get a negative a. So that's nice. That tells me that a has to be negative 52. And then what's another convenient x value? 8. So if I let x equal 8, then 8 squared is what? 64 plus 3 is 67. This becomes 0, and then I have 8 minus 1, so I get b is 67. So apparently I have the two values of a and b that will work. So that means I can rewrite my original integral. So we had the integral of x cubed plus x squared plus 3 over x squared minus 15x plus 56. Claim now is that is negative 50 what? 2? And that one's the x minus 7, negative 52 over x minus 7 plus 67 over x minus 8 with respect to x, which we can nail both of those with logarithms as the antiderivative. Now, before I continue that, I just want to show you the other way of dealing with what we have. So let's go back a page and put a page in between. So we eliminated the denominators. So we have the numerator, x squared plus 3 is equal to a times, let's see, what was that? The x minus 8. plus b times x minus 7. So the other way to handle this is to distribute through on the right. So that'll give me an ax minus an a8 or 8a plus a bx minus a b7 or 7b, however you choose to write it. And if I reorganize these by putting like terms together in terms of x, then these two right there give me an a plus b as the coefficients of x. And as far as my constant term is concerned, I just have a negative 8a and a negative b7 for the constant terms. This side of the equation has to match up with that side of the equation over there. So is there a x term on the left side? There's an x squared term on the left side, but not an x. Right? There's no linear power of x on the other side. So that means the a plus b has to add up to 0. And then the negative 8a or a8 minus b7, that's got to add up to 3 because that's the constant term. And then we can solve that system of equations. So no matter what, you're going to get a system of equations. Sometimes this method is easier. Sometimes this method is easier of picking convenient values. It kind of depends. It can go either way. It's hard to say which one. The book goes over this method right here, where you combine, you multiply everything together, and then you combine like terms in terms of x, and you try to match those coefficients up on the other side. Okay. And it's up to you which one you want to use. I tend to like this one better, where I pick convenient values. All right, let's try another one. Let's see. How about, ooh, that one was a wild one. Yeah, let's do this one. So integral of 11 over x squared minus 1 squared dx. First step is the denominator factored. Yeah, so if we can factor the denominator, we have to. Otherwise, it gets messy. So note x squared minus 1 is really x minus 1 times x plus 1, and that's being squared. So what I have here is the integral of 11 over x minus 1 squared times x plus 1 squared. Because x squared minus 1 is x minus 1 times x plus 1, difference of two squares. If that was an x squared plus 1 in the denominator, that would be an irreducible quadratic, and we would just move on. It's not factorable, but this one is. So here I have linear factors. Okay? And the partial fractions for linear factors say you're going to have, because of the second power, you're going to have two sums for each linear factor. So 11 over x minus 1 squared, x plus 1 squared, should be equal to a over x minus 1 plus, let's call it b over x minus 1 squared plus c over x plus 1 plus d over x plus 1 squared. Yeah, so we have to have descending powers of each factor of the bottom. So if that were x minus 1 cubed and an x plus 1 cubed, we would have one more fraction for each of these. So we'd have 6 constants to figure out. Okay. Yeah, so that's when, so a lot of times with these, what we do is we get them organized and we end up with a system of equations, and then we just apply matrix stuff to it. So there's some of these problems where what you're going to want to do is just find the system of equations and then whip out a matrix solver and have it do it for you. Okay. I assume you guys all have done matrices before? Some yes, some no? Okay, so we'll take this one both ways. All right, so once I determine I factored the denominator thoroughly and I found each fraction that I can work with, then I have to multiply through the common denominator to eliminate all fractions. So write down what you think that's going to look like, and I'll put down my version. In some of these problems, you might want to turn your paper sideways because you're going to need more length. I'm not sure I can fit this on this board unless I write real tiny. Oh yeah, I can half it and shrink it, right? You want to, yeah. This section's going to use a lot of paper. All right, so here's what I think we have. Oh, I pulled it off the screen. Darn it. I'm going to undo all that mess. Thought I shrunk it. Oh, wrong device. Yeah. Okay, let's try this again. Am I shrink? Okay, now I'm shrinking it. Okay, so then I can fit my plus d times x minus 1 squared. All right, so I had to multiply both sides. We get some cancellation each time. So I lose an x minus 1 here. I lose an x minus 1 squared there. I lost an x plus 1 here. And I lost the x plus 1 squared there. Okay. Next, we decide either to start picking convenient values of x to make stuff go away. Now, one problem, how many coefficients do I have? 4. How many convenient x values do I have? 2, which means I'm then going to have to start choosing inconvenient x values. Okay. That, you know, like, well, we can like what's an inconvenient x value? Well, convenient ones are 1 and -1 because they'll wipe stuff out. 0 isn't too bad here if you pick 0 as a value of x, and I think the next best value of x would be 2. So that's one way to attack it. Other way to attack this is to multiply out each of these and then reorganize everything in terms of x cubes, x squareds, x's and 1s, and then try and match coefficients with the other side. They're equally hard. I did it both ways. Each took me a page. Which shall we do? Let's start with convenient x values. Okay, the book shows how to do this with the collecting terms, and we can do that tomorrow or later today. All right, so for me, my convenient x values would be x equals 1 is a nice one. So if x equals 1, then I'm going to end up with 11 equals, anytime there's an x minus 1, that whole thing zeroes out, which is nice. That's why I call them convenient. So the A stuff is gone. The B's are not. 1 plus 1 is 2. 2 squared is 4. So I'm going to get a 4B. Let's see. The C stuff is gone and the D stuff is gone. So now I know what B is. All right. B is equal to 11/4. So the hardest thing about this is the algebra and the arithmetic. The first time I did this problem, I wrote 4/11 by mistake. So everything else went to heck. Oops. So be careful. All right, other convenient x value is -1. So there we're going to get 11 equals, let's see, if I plug in -1, the a stuff goes away, the b stuff goes away, and the c stuff goes away. All that's left is d. -1 minus 1 is -2, squared is 4. Oh, that's nice. I get a 4d. So d, like b, is 11/4. And I'm going to slide these guys up just a little bit so we can fit the next two. Hopefully that'll be enough. So we're out of convenient x values, so we accept the next best things, like 0 is a lovely number for x here. So if I let x equal 0, I'm stuck with everything. So let's see, we're going to get 11 equals -1 times 1 squared, which is -1. So I'm going to get a negative a, right? Here I will get 0 plus 1 is 1, squared is 1. I'm just going to get b, but I know b is 11/4. So I'm going to get plus 11/4 there for b. And then let's see what's happening with c here. C gets to be 1 times -1 squared. So I'm just going to get a plus c. Is that right? I think so. And d, 0 minus 1 squared, is just d, which is 11/4. So let's see, cleaning that up a little bit, 11/4 plus 11/4 is 22/4, or 11/2. We want to take that to the other side of the equation here. So this equation right here is going to turn into 11 minus 11/2 equals -a plus c. And 11 minus 11/2, that would be what, 22/2 minus 11 is, it's 11/2 again. Well, isn't that sweet? So this part right there is 11/2. Okay, next value I could come up with that was reasonable was 2, because 2 minus 1 is 1. That's not too bad. I think you can make an argument for -2 too, but negatives cause trouble if you're not careful. How are we doing on time? Good. So I'm going to go for x equals 2 as my next alternative value. And so I'm going to get 11 equals, let's see, 2 minus 1 is 1, 2 plus 1 is 3, squared is 9. So is that a 9a? For b, 2 plus 1 is 3, squared is 9b. And b is 11/4. So I think here we will have what, 99/4? 9 times b. Plus, let's see, c is going to be a 3 times 1 squared. So I get a 3c. And d, 2 minus 1 is 1. 1 squared is 1 is just d, 11/4. So I think I got those right. Do you guys agree with those values? All right, so careful arithmetic. Cleaning this up, let's see, 99/4 and 11/4 is what, 110/4 or 55/2? So we're going to have 11 minus 55/2 equals 9a plus 3c. 11 minus 55/2, so that'd be 22 minus 55 is -33/2. All right. All right, so let's see if we can get this right. So this isn't too bad. Instead of having a system of 4 equations and 4 unknowns, we narrowed it down to a system of 2 equations and 2 unknowns. So yes, we can divide out a 3 on that, right? Because we have -33/2 and we get 3's on each side, yeah. So the first one was what? -a plus c equals 11/2. And the other one, if we divide out the 3, is going to be 3a plus c. 3a plus c equals negative 11 halves. If we divide the 3 out, that feels pretty good. And like, whenever I'm doing my homework, I try to do as much in my head as possible. However, that always leads to mistakes, like me writing things like 11/4 instead of 4/11 or vice versa. All right, what do we have here? I guess we could subtract these from each other and the c's will go away. Or we get c equal to 11 halves plus a. Yeah, so whatever your technique is that you like for cleaning this up from here, I think I'm going to do a subtraction. So feel free to do a substitution if you prefer. So that's going to give me what? Negative 4a's. C's go away. Equals 11 halves plus 11 halves is 11. And so a is negative 4/11, I think. No? Negative 11/4. I did that earlier today. Negative 11/4. Thank you for paying attention. And then C is going to be 11 halves plus A. And so that's 11 halves minus 11/4, which is 22 minus 11, which is 11/4, right? Anyone else get that? All right. Am I okay, Stanton? Anyone else getting those numbers some way or another? Got a few nods. Okay, so finally, we are able to throw these numbers in. So let's see. Help me remember. Let's see. The original integral was 11 over x squared minus 1 squared. And our belief is now that this is equal to the integral of a is negative 11/4. Is that right? So negative 11/4 over x minus 1 plus b. What's b? It's 11/4 too? 11/4 over x minus 1 squared. C 11/4, right? They're all 11/4 or the opposite. X plus 1 is this denominator. And you got to make sure you match the coefficient with the right denominator. Otherwise, it doesn't work. And then D was positive 11/4, is that right? Only A was negative. Okay, x plus 1 squared, close dx. 11/4 is in everything, which is nice. That doesn't always happen, but sometimes it does. So I can pull that 11/4 out and then start thinking about antiderivatives. Okay, antiderivative of 1 over x minus 1 be the natural log. And we have a negative, yep. So negative natural log of the absolute value of x minus 1 plus x minus 1 squared is a lot like u squared, because the derivative of x minus 1 is just 1. So that's nice. And what's an antiderivative for u to the negative 2? Nope, wrong way. Increase the power. U to the negative 1 divided by negative 1, or times negative 1. So then I'm going to get a negative 1 over x minus 1 for that one, plus natural log of the absolute value of x plus 1. And then similarly over here, we'll have plus negative 1 over x plus 1 plus c. Did I do that right? Yep. Well, the C, remember the C we got the other day? It was kind of complicated. So yeah, sometimes the C is tricky. And then we can clean this up a little bit by combining like things, like the natural logs can come together. So I could say this is the natural log of x plus 1 minus the natural log of x minus 1. So those will come in as a difference. So let's switch colors, clean this up a little bit. My guess is the online homework might accept this. So I got my 11/4 hanging out front. And then in here, those two, I believe, could be called the natural log of the absolute value of x plus 1 over x minus 1, because the x minus 1 has the negative on it, so it's the divisor. And then I could add these two together with a common denominator of x plus 1 times x minus 1. So if I do that, this one would have to be multiplied top and bottom by x plus 1, and this one by x minus 1. And if I factor the negative 1 out, I will have a minus. Oops, I wrote something wrong. This should be an x plus 1, right? Is what it's missing. So x plus 1 plus x minus 1 is just 2x, isn't it? Because I'm factoring out the negative. So I'm just going to have in the numerator a 2x, and my denominator is x minus 1 times x plus 1, which I'm going to call x squared minus 1. And I don't know if I can use any less ink than that. Whew. So this isn't bad. What did we do? 3 problems today? That's about similar to yesterday. So, for example, if I use the other approach, where we multiply all the x plus 1s and x minus 1s out and then collect like terms, I found when I collected like terms that A, no B, plus C, no D was 0. A plus B minus C plus D was 0. Negative A, and I can show you how I got this tomorrow. 2B minus C minus 2D was also 0, and negative A plus B plus C, whoa, extra mark. Pen was freaking out. There we go, where was I? B plus C plus D was equal to 11. And so I could rewrite that as a matrix. You guys remember augmented matrices, where you take the coefficients up there of A, B, C, and D. So that would be 1, 0, 1, 0. And then usually we draw a line there and put a 0 there. This would be 1, 1, negative 1, 1, negative 1, 2, negative 1, negative 2. Oops, I forgot the numbers on the other side. 0, 0, and negative 1, 1, 1, 1, 11. And if you plug this into a computer that can put it in reduced row echelon form, I think it's usually written like that, reduced row echelon form. That means you have 1s along the main diagonal and 0s everywhere else. It, on this side, should be the solutions for A, B, C, and D. So let's see. I'm sure online there are matrix solvers. Matrix solvers. Calculator has a nice, if anybody have a TI on them, TIs do this super easy. Let's see. Linear equation solver, linear equations calculator, matrix calculator, maybe. Wolfram Alpha can probably do it too. Let's see. On the TI, you would go to the matrix menu, and then you would edit, say, matrix A to be a 3x4 matrix. Oh, that's not what I want there. Back. So it has, sorry, this would be a 4 by 5 matrix. And then you would type all of these numbers into A. And then you would go to, after you do that, you save it, you go to matrix math, and you say, do RREF on matrix A. And then it'll spit out a new matrix that has the answers we want on the edge. Now, I don't have a TI on me, so I can't do that. That's why I'm trying to find an online matrix calculator. Let's see what the first one does. Enter the left side, enter the right side. Oh, let's see, how do we enter it? Show instructions. Spaces, okay. So if I enter, does anybody have those numbers written down? Oh, I got them right here. 1 space 0 space 1 space 0. Right-hand side was a 0. And then I guess I'm going to do a new line probably. And then a 1 space negative 1 space 1. And then a 0. I've never used this one before. I meant to look these up before I came to class, but I didn't have a chance. 2, negative 1. I decided it was way more fun to do it by hand. Negative 2, 0. And then negative 1, 1, 1, 1, 11. And solve. Yep. Is 11 force 2.75? Yep, it is. Yeah, so here's my negative, blow that up. Negative 11 force, 11 force, 11 force, 11 force. It gives it to me as decimals, unfortunately, but the TI can do the same thing by typing in that whole augmented matrix. And an augmented matrix is where you take the input matrix and combine it with the solution matrix in one bigger matrix. So what we do is the new matrix, after we apply all the row calculations, looks like 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, and the augmented side are all my solutions. Negative 11 force, 11 force, 11 force, and 11 force. So my advice is if we do have one with a ton of coefficients, see if you can get it into a system of equations and then find a matrix solver on the TI. I'll see how Wolfram does it. It might do it well. And get it to spit out what's called reduced row echelon form, which says A, B, C, and D equals respective numbers on the other side. You got yours to work on the TI? Yeah. So I'm not going to... The hard part here is getting everything set up, then finding the coefficients. Most, I don't know if this is true, I'm going to guess 75% of these problems, I find the coefficients slightly easier by picking convenient values of x, meaning my matrices aren't as complicated in the end. Now, I could be wrong. I could have just accidentally picked problems that led me in that direction. So we'll do more of these tomorrow using the books method and see what happens. So that's it for now. Have fun.